All right. Um,
Uh, I don't know for Murray and Pinakini if you have means if you attended our discussion. Um, did you attend the discussion of
Last
Perceptron?
one I did not attend, Pavan. I wasn't well actually. Uh,
Okay.
so I have some basic idea, may not be like in depth or internals, but yeah, some basic idea
Yeah.
I have.
Okay. Okay, let me start on that. But yeah, before that, recently I was looking at something called graph rag. Okay, I was implementing that, but I am not fully internally. I am gone through it, but that is one of the things. I mean, that is something like which is like in few cases better than the vanilla rag what we are using. Probably sometime we'll talk about that also once I have more. I mean, I have bit of understanding, but I think bit of deeper understanding may be required uh, to explain it better. Okay.
okay, okay. Yeah.
Yeah, that's also something maybe coming up in the interviews and all. I just wanted to let you guys know, at least like if you can see it and what is graph rag, how all those things, Neo4j. Uh, so maybe if you're preparing for the interview.
Okay, okay.
Yeah, so uh, yeah, first of all, we discussed last time that why deep neural network and in the sense what is the difference between traditional machine learning algorithms and deep neural networks. So in the case of traditional machine learning, right, we have the clarity why it works. If we get an output, we know why we are getting that output, and uh, the smaller problems or the lesser complex problems can easily be solved with the traditional machine learning algorithms or models. And also like when you know the features, okay, or you say unstructured data, or better think of like when you know the features, how each feature affects the output, then usually we will go with the machine learning models. I mean, when the problem is lesser complex and you know the features, you have maybe smaller set of data, smaller set in the sense even millions of data. We will go with the machine learning. But in case of deep learning, uh, few things actually. One is that using deep learning, we can approximate any problem. We can try to approximate the output for any problem using the deep neural network. And deep neural networks, you don't need to know the features. Okay, maybe in the future classes, right, we'll uh, talk about the features regarding to the deep neural networks, like how deep neural network itself is extracts the features. Okay, but for the machine learning, we need to extract the feature and train it. But for deep neural network, we don't need to do that. So, and for the deep neural networks, we need a lot of data. Suppose ML needs millions of data, we need millions of data, like tens or hundreds of millions of data or billions of data. Okay. Um, what else? Difference. Yeah, you don't need the label. You don't need to know the features for the deep neural networks training. And deep neural network is costlier. Lot of computations and too many computations. Too many parameters and lot of computations. Resource intensive, data intensive also. Let me know if any questions. Vinul, you also, if anything I'm missing, can add. You
Yeah.
can add.
All right.
Yeah, that's where the deep neural network comes in. Kind of, I am fascinated with the deep neural network. Why? Because it is actually mimics the brain uh, for a certain extent. Okay, say brain has the neurons, deep neural networks also has the neurons within it. But for the like AML term, we'll call it as a perceptron. Okay, but I think neurons is also being called. Again, these are all yeah. So how our brain works, right? There is some 86 billion neurons in the brain. So if you uh, create a network of neurons which is similar to how the brain works, we can actually solve any problem. Means solve in the sense approximate the solution for any problem. Okay, even brain does the same thing. Brain actually approximates everything. Okay, so if your brain sees a cat, it actually approximate. Okay, this might be a cat. Okay, it's not like 100% it is a cat. Okay, but yeah, we perceive it as a okay, it's a cat because probability of it being cat is high. So sometimes ambiguous images also you see, right? Like it might be a dog or cat kind of mixed. So that time, yeah, you will feel that probability. Okay. So each neuron in the artificial intelligence terms, we'll call it as perceptron or neuron also. It's kind of interchangeable. Uh, so, what does each neuron do? Is it actually has the summation, two parts actually. Each neuron has the two parts. I'm talking about the deep neural networks now. Each neuron has two parts in it. One is the linear function, which is actually summation. Okay. So you have a features or the inputs x1, x2, like xn. Yeah, I think I better call it as inputs x1, x2 to xn. So when you send these x1, x2 values, maybe 1.0, 1.2, or zero point 0.2, like that, each input will be multiplied with certain weights, and it will be some added actually. I mean, um, all it's like this: x1 into w1 plus x2 into w2 plus x, like that, till xn into wn, all summation plus 1 into bias. Okay, we'll come to the bias also. I think last time we were talking about bias, actually why bias is required. Bias is for the generalization, so that we will avoid the overfitting. That's the main intention. Okay, that is the first part. Second part is the activation function. Um, so this is, you can think of like some threshold. Okay, say value of z goes above 0 means you will make the output as 1. If it is below 0 means you make it as output as 0. That kind of function, activation function. Okay. So it has two parts, summation and the activation function. Activation function can be non-linear also, like there are multiple activation functions: sine, sigmoid, ReLU, Tanh. These are some of the activation functions. Okay, and going to the next. Okay. Let me take this. Yeah, this is what I was explaining. Okay, now the thing is that this one perceptron, right? This one perceptron can can solve a simple problems like a NAT function. Sorry, no, not NAT, not or AND function, or even the OR function. Okay, the simple problems can be solved like that, Boolean functions. So this not and or are all linear functions. So when I say the linear, I need to explain why it is linear, right? Okay, last time we had a figure. Yeah. So yeah, I think I'll take this example. So if you plot the AND gate, what is the AND function? Do we have the... Okay, it's okay.
There it is,
Type
45.
55. Yeah. Yeah, this also is fine, but if it is in 0, 0, it would have been easier. Okay, and will be output will be 1 only if both are 1. Otherwise, it is 0 or -1. In this case, we will take it as -1, and we are putting the input values as -1 and 1. So the output also will consider it as -1 and 1. Okay, when both inputs are 1, the output is 1. So if you plot that right here, so when both are -1, the output is what is that? Output is 0, right?
Yeah.
When both are 1, it is
Then
1.
yes.
When one is 1 and other one is -1, it should be uh, again -1 or 0, whatever. So here I think this is wrong, right, Vinal?
This is
The
perceptron or
color is...
orgate?
No, here the color, why the
Color.
color is blue? Color is blue, why here?
This is orgate color.
Blue means
That's
1.
why. That's
Oh,
why.
this is OR gate. Sorry.
Yeah.
Yeah, I was looking at the NAND gate. Okay, I think let me go with this one. Okay, OR
Orgate is
gate.
better. Yeah.
Yeah. So, see, we can solve this problem of simple linear problems with one perceptron. So, if you see here, when the inputs are 0 or -1, the output is marked as -1 with the red color. So, this red means -1, blue means 1. Okay, so when you plot it in this two-dimensional graph, you see that in this spatial dimension, 2 dimension, you can separate the blue colored points from the red colored points. That means that it is linearly separable. Okay, so that means that you can solve that problem linearly, in the sense something like x1 plus x1 into x0 into w0 plus x1 into w1 plus x2 into w2, kind of simple solution. Okay, equal to 0, that kind of, and then solve it. Okay, so you got it right. So it can be solved with one perceptron. That calculations are there. I am not going into that calculation. You'll get a good idea if we go into the calculation, but I think it will take long time. Maybe we can separately discuss on that. Okay. So the idea is that if you linear problems can be solved with single perceptron. Okay, where you can separate this say one set of values from other set of values in the spatial dimension. Okay, if you have any questions, let me know. I don't know whether I am making sense.
This is fine. This is classification problem you're explaining about. Is that
This is classification problem. So what happens is that, say here, x0 is always 1. Forget about that because that's a bias. So now x1 and x2 is these values 0, 0, 0, 1 or 1, 0. But yeah, 0, 0, 0, 1, 1, 0. So when you pass 0, 0, your OR gate should give 0. Okay, so the perceptron should give 0. So you will arrange your weights such that Whenever you give 0 0, it will always give 0 output. Whenever you give 0 1, it will give the 1 output. Whenever you give 1 0, it will give 1 output. Like that, you will set the value. You will set the value of W1 and W2. Okay. And then you will also set the threshold, which I mentioned previously. Okay.
Yeah.
Uh,
In the
this
real
threshold,
sense,
this threshold, if the z is greater than 0, if the z is any value, you can set actually greater than 2 or less than 2, something like that you can set depending upon your w value.
this is weighted summation, no?
Weighted summation, correct.
Okay, okay.
So where did it go?
I mean, here, like you are saying, no?
Huh.
If you open the perceptron for orbit, here, x0 is
Hmm.
always 1 because it maps to bias. So we ignore that. And x1
Yeah,
and
we
x2
ignore
are your
one.
two inputs for the OR gate, which actually
Correct,
matters. And we
correct.
know
This
how
OR
the
gate is, yeah, this OR gate is, you can consider it as some perceptron, and inside the perceptron you have the summation and then the activation function.
Okay, yeah. So this OR symbol
Yeah,
is like a perceptron having the weighted summation and the activation function, the processing unit, the node of the perceptron. Okay. So
yeah, yeah.
we expect the perceptron, the OR perceptron, to give the results which we see in the table. And for that,
Correct, exactly. Yes, yeah.
we actually train the not we set the
Yes.
weight in such a
No,
way.
no, you train actually.
Exactly.
Training is the correct word, correct
Yeah.
word.
Yeah.
So here also you will do the back propagation and all. It is very simple to understand. If you maybe we will go through that sometime.
Yeah.
Um, Maybe I'll go through now only, but don't expect me to be like perfect in explanation here. I'll just give the hint how it works. Okay.
So
So okay,
that is your
this
system
is
prompt, okay?
which is system from.
Oh, this is an AI joke. I wanted to make an AI joke.
Oh, okay, got it.
Okay,
Okay,
all right.
so yeah, understood, understood. Okay, so this is for a NOT gate. Okay, this is a simple NOT gate, not even the OR gate. It's a simple NOT gate. So whenever you put -1, you should get the output as 1. So x1, you have only one input here. Okay, and one input and one bias. Okay, W0 is your wait a second. W0 is your bias.
Yeah.
Okay. W0 is your bias. Now, X1 is the only input you have. W1 is your weight for the input because you have only one input. Now, when you input -1, you should get 1 as the output. T is the actual output or the ground truth. Okay.
Hmm.
Sorry, not actual output, the expected output.
The ground truth, you mean? Yeah.
The ground truth. Which is the
Yeah.
ground truth? Am I correct? Am I correct? I think I'm correct. Yeah. So T is the ground truth. Why it's
Yeah.
put as
T is the
actual
ground
output
truth.
here
It
then?
says the next to compute, no? Delta W is equal to T minus hat Y hat. Y hat it is the prediction. Ground truth.
Correct.
Yeah.
Yeah. So uh, okay, so when you give -1, you will expect 1 for the NOT gate. At first, you will keep W1 and W0 to any random value. Okay, any random value. For here, we will keep it as 0. Okay, and this eta is the learning rate. Okay, how much it should learn in the back propagation. We'll come to the back propagation. Okay, now initial weights are 0 and 0. Okay, now you calculate the z value, the summation value. So that is like 0 into 1. 1 is the x0. X0 will always be 1. So W0 into x0, that is 0 into 1 is 0. And then x1 into W1, that is -1 into 0, it's a 0. Okay, we got 0. So next you will have the sine function. Okay, sine function works like, I think it is below 0, it is -1. It is above 0 means it is 1. So here it is, since 0, it is -1. Okay. So is that matching? We got -1, but we expected 1, right? So that is not correct. It's not correct. So what we do is that next there is a formula to compute the delta. Delta is kind of a loss. Okay,
The
not
loss
loss.
value.
Uh,
I mean the difference between the actual value, the ground truth and the prediction.
Yeah. So see here, T is the actual value, sorry, ground truth. Y hat is the actual value. So we minus that, okay, into the X. X is the input. Here it is X1. So -1. Okay. And eta is the learning rate. This is a formula which gives us the delta value. Okay. So what is delta? Will again come that, but we'll calculate this delta value now. Delta W1 we'll calculate. Okay, so the same with the same formula. One is the eta here. We considered one as a learning rate. Learning rate is 1. Then here 1 minus of -1. I think, yeah, 1 t is 1, and minus of y hat is -1. So 1 plus 1 it became, and then x is again -1. X1 is -1, so it became -2. Okay. Now, this delta is the difference, okay, which
Gradient.
needs to be applied. Sorry?
The gradient, right? We can call it the gradient. I mean,
I
during optimization, when we change the weights by some gradient, we apply this gradient to the
I honestly, I forgot to, I mean, yeah, I mean, I don't want to
That's okay. Let it
tell
that down
incorrectly.
for
Okay,
now.
so so I don't remember. See, gradient is where we know the directions. Okay, maybe minus is the direction here, but I don't want to
Okay.
confuse, or I don't want to say wrong. Okay, so let's consider this as a difference where which we need to apply to the existing weight, so that weight moves in such a direction such that your output becomes near to the ground truth.
Hmm.
Okay, so now what happens is that I think I better explain this. I don't know. Okay, let me try. Okay, so you have lot of neurons here, and lot of neurons is having some weights. Okay, so now you put some x0, x1, x2, any problem. Okay, some problem. You are solving some problem, and you are inputting two inputs here. Okay, and your expected value is something like 5. Okay, but this is a ground truth expected, but you are not getting 5. You are getting, say, 500 or 512. Okay, so you have initialized with some weights here, W1, W2, like that, several neurons are there. Okay, think this as a brain or deep neural network. Uh, so now what you will do in the deep neural network is that now for the same inputs, X1 and X2, you need to tell these deep neural networks, okay, whatever your output 5 is wrong. Okay, but the output is actually 512. So how do you tell is that you calculate that delta, whatever we showed here, right? We calculated here. Then, where did it go? Then you backpropagate in such a fashion these weights, right? These weights will rearrange itself or move towards a certain value, so that whenever you give x1 and x2 certain value, you get the expected value. Means you are moving your weights such that you get the expected output. Okay.
Yeah, right.
I hope I made some sense there. I
Yeah,
don't know. If didn't understand, let me know. Okay. That's
this I
something
explained in
important
fine
or
tuning as well. This I explained in fine tuning as well last week, wherein when you have a ground truth, you know what the actual value should be. Then you make the prediction through the deep neural network. Then you compare the prediction and the ground truth and see and do the loss calculation. And based on the
yeah,
loss you calculated, you have to back propagate that loss in such a way that the weights get adjusted in such a way that your loss comes down and your prediction becomes closer to the ground truth and
correct.
keep on iterating in the same loop and you will land at the ground truth. Okay, but that is
Yeah,
practically unrealistic
yeah.
to achieve the ground truth in most of the cases,
This,
but here it is. Okay, fine.
yeah, this is exactly why I don't get selected in interview. I am very bad at explaining. So Vinal, you did
Eh,
a very nice job actually.
yes,
Okay.
I can use that. Okay.
Okay, so now we got the delta, right? Um, so now we actually add that update the weight actually add that delta to the existing weight. The here W new equal to W old plus delta W. So we make that W. So if you see here, eta is 1. Here we are not uh, or how do I put here whatever the difference is there, we just update it. Eta can be point 0.2, point 0.4, point 0.5 also, so that we don't want to make big changes. Okay. So we don't want to make big changes. That again, you will understand why we don't want to make the huge changes, because we here it is a simple problem, but in deep neural networks you are training with multiple data. So for one data, if you are making a big change, it might affect the um, weights for the other data where it has learned from the other data. So that you will understand going forward why learning rate is required. Here, learning rate actually doesn't matter in this problem. So that's why they have kept it to 1. So yeah, you update the W1, and same thing you can do for the W0 also. Okay, now you got the new weights -2 and 2. Okay, now with that -2 and 2, you again do the same inference first, like you change the weight, then again you input the x1 as here they have taken as 1, you input as 1, your expected is -1. Okay, then you with the new weights you calculate what is the output it is coming, it comes as -1. That is correct. Okay, that is correct, but you still do the delta, because this is training. You still need to calculate the what you say delta, but delta will be 0, because here in this case we don't have the change, we got the expected. Okay, so there is no delta, so the values will remain the same. Now you check with whether this -2 and 2 will work for the x1 as 1 -1 also, because it worked for 1. You check it works for the 1 -1. So then you check with that new weight -2 and 2. You see that once you calculate, you will get the output as 1. So when you input -1, you will get the output as 1. So that is fine. Okay, there here also no delta. Delta is 0, so no update to the weight. So when this weight is -2 and the bias is 2, your perceptron will work as a NOT gate. Okay, with this sinusoidal
Activity.
activation function. But this need not be always -2 and 2 for the this one. There can be multiple values. Okay, this -2 and -2 are -2 and 2 are one of the multiple values for the NOT gate. You have different threshold, the different values, different sign activation function also. You can achieve that. Yeah, I don't know if. Hey, Marie Arun Pinakini. got anything or?
Not completely, Pawan, for me. Like,
Yeah, not 100%, but yeah, I'm trying to follow. Uh, Probably,
Okay.
Pavan, so I think we have to do some homework also. It's not like we can get everything without some
Yeah,
basic.
this is bit of that's why I was thinking. I just wanted to explain to
Until that
give you
weights
a hang of it.
summation, I was okay, but coming here, I think in between I lost, I mean, somewhere.
Okay. So
Yeah.
just to understand that, okay, this is a learning. Okay, this is a
Yeah.
learning. So
Mhm.
you first keep a random weights and see what is the output it comes, whether that is near to the actual output or it is far away from the actual output. You take a difference. That is, you calculate the loss. Okay, how much it is differing from the actual ground truth, means the expected output. How much the actual output is uh, varying from the ground truth. Okay, expected output. So then you update the weight in such a way that that loss is minimal. Okay, so that next time when you input that value, your output will be nearer to your expected value. So it is learning. You're learning the weights actually here. What is the correct weight for, in this case, for not gate? Okay.
Mm.
What is the weights if you uh, put the perceptron will act as a not gate here. Okay. That's what it is learning.
Mm.
Okay.
Mm.
Uh, yeah, we can discuss this also again sometime. Uh, okay, but let me.
I
If
think
any other questions, then
So,
let me.
like one slide or something that we learned now, maybe this not gate itself, if you can share, then probably any gate that you just explained.
This I can share. I think I already shared
Yeah,
with
one
Vinal.
slide, maybe
Yeah,
a
only
screenshot of
thing
it.
is that, yeah, since it is bits, this
You
one.
just share the screenshot only, Pavan. Don't
No,
share
no,
the
that's okay.
slide.
I'll share
Mm.
that. Not an issue. Which one actually? Which any
The one
slide?
that you just explained
not
it, I
gate.
think not gate is the one you have taken example.
Okay. Yeah.
Yeah.
OR gate perceptron and for classification and not gate for calculation.
Yeah. Okay. So
Okay.
now one more thing to understand